Hello and welcome to Starfish Maths. My name's Sarah and today I'm looking at parametric equations. This is a topic, it's quite advanced. It brings together skills from lots of different areas. So you need to be familiar with differentiation, logs, trigonometry and lots of algebra skills. But don't worry, I've got videos on all of those, so check them out if you need to. As ever, please do grab a pen and paper and do the work yourself, pausing the video and rewinding or skipping around as you need to work at your own pace. Let me know how you get on in the comments below, and if you want any information about small group masterclasses or private tuition or anything else, don't hesitate to get in touch at starfishmaths@gmail.com, or you can visit the website starfishmaths.com or Instagram. I hope this is helpful, and if you're ready, let's get started. So, parametric equations. These are just another way really of describing a graph or a set of points. So normally you'd be used to a Cartesian equation, and that's the fancy name for an equation that's just got x and y in it. So the very simplest being a linear equation, y equals mx plus c, or any other kinds of equations. So now you're a little bit more advanced, you'll see parametric equations, which are just using another parameter, in this case theta. Theta is a parameter, not to be confused with x and y, which are variables. X and y are on the graph, which change, and theta doesn't. It just connects the two equations together. So this is a simple example just to show you what I mean. If we've got x as sine and y as cos, then we know the identity, or you should do anyway, that sine squared plus cos squared is 1, and we can use that identity to connect these equations. Sine here is x, so that'll be x squared, and cos is y, so that's y squared. So we can turn these parametric equations into that Cartesian equation, and then you can see and hopefully recognise what that graph would look like. It would be a circle, centre of the origin and radius 1. Just like you get to know that that is a circle in Cartesian, you can get to know in parametric equations that that's another simple way of describing a circle. And parametric equations have all kinds of benefits. They can sometimes simplify the algebra and make them a bit more easy to handle. So let's jump into some questions and have a play around with some parametric equations, and hopefully you'll get a flavour for what I'm talking about. Okay, here we've got our first question. So here's some parametric equations again. I'm using t as the parameter this time. That's quite a typical letter to use. And we've got a question here in two parts. Find where the curve crosses the x-axis and another line. So let's take the x-axis first. Hopefully you already know that at the axis, x or y-axis, something is 0. So at the x-axis, whenever a graph crosses the x-axis, y is 0. So to do part A, you just need to set y as 0, and that's that simple. And we'll take the parametric equation and we can solve that by factorising. So t comes out as a common term is what I'm trying to say, and we can factorise that again because that's the difference of two squares. So that gives us 3 solutions. Once we know t, we're trying to find the coordinates. Well, we know that y is 0, but we want the x coordinates, so we can put this back into the parametric equation for x to find those coordinates. So we're putting 0 into this here, 4 times 0 minus 1, and the other 2 as well. So we've got a repeated solution here, so probably the curve is crossing and then coming back and crossing again. I don't know what it's doing. I'm not sketching this curve today, but that's a repeated solution, and we've got this one here. So we've got 2 different points where it crosses. We've got minus 1, 0, and then we've got this other repeated one, which is 3, 0, and those are our solutions for part A. Okay, so that's how to find where a curve crosses an axis. Hopefully that makes sense. And we can also find where it crosses a line. So we've got here a Cartesian equation for a line, and hopefully you know, again from your work on coordinate geometry, that when stuff on graphs cross, they're equal to each other. It's kind of simultaneous equations where all the equations hold up is at the points where they cross. So we want to see where these equations hold with that equation. So the obvious thing to do there is to use these in that equation, substitute them in. So where we've got y, we're going to use t cubed minus t, and same for x. Let's substitute those in. Do have a go at that yourself. So there we've got that linear equation, but we've replaced the x and the y with the parametric equations. Now we can try and solve that. Do have a go. Here I've just divided by 4 because that was the common term, and I'm going to take t out as a common factor, and that should factorise. Okay, so there again we've got 3 solutions. Okay, so we found 3 points, 3 values of t. And again, to get the coordinates, we need to substitute them back into x and y to find those coordinates. Okay, so just writing that over here, I'll substitute those in. Okay, so our coordinates are -1, 0, 0, 3/8, and 15, 6. I hope that makes sense. I hope that's pretty straightforward now seeing that. Let's have a look at another question, see what else we can do. Okay, this one is actually a past exam question. So this time we're given the shape of the curve, and we're given a little sketch of that. A and B are where it crosses the axes, and we're asked to find A and B, so those coordinates there. Again, we've got some parametric equations here, so hopefully you can have a go at this. It's similar to what I did in the last question. We need to set x as 0 for A and y is 0 at B and solve those to get the coordinates. Do have a go. Okay, I hope you followed that. Setting x as 0, I got that t was 2. And put that back into y equation to get 3, and that's the coordinate. Let's have a go at B. Here y is 0, so it's the same sort of process. Okay, I got that 2 to the power of t is 1, so that tells me that t is 0 this time. So x must be 1. Okay, so another thing you can do with parametric equations is you can do everything you can do with normal coordinate geometry. So something is finding the equation of a tangent or a normal. So we'll take a normal and find the normal at A. So I'm sure you remember that that means finding the equation of the straight line which is perpendicular to the gradient at the curve at that point. So we're finding the equation of that straight line. To find the equation of a straight line, you need 2 things. You need the gradient and you need a point that it goes through. We've already got the point it goes through. We've got the coordinates at that point A. So we just need to find the gradient. So here is a chance to differentiate the curve using the parametric equations. The way to differentiate is differentiate both of these separately and then use the chain rule just to connect them. So if you've done the chain rule, then this should feel, hopefully, very manageable. So we've got dx by dt when we differentiate this one, we'll get a half there. And dy by dt, here you need to know how to differentiate exponentials. Anything to a power, when you differentiate that, you'll get the same again multiplied by log of that base number, so log of 2. So that's a little reminder if you'd forgotten how to do that, just remember. And now we want to get dy by dx to get the gradient. So remember your chain rule. All the skills that are involved in this video I have covered in previous videos, so if any of this feels a bit weird or unfamiliar, do check out some of my other videos. But here's the chain rule. We've got dy by dx is what we're aiming for. So we can set it up like that with the dt on the top and the bottom, because those two will cancel out to give us dy by dx. Dy by dt we have, and dt by dx is just the reciprocal of that one, so it'll be minus 2 over 1, so just minus 2. So let's have a go. We've got 2 to the t times ln 2, and then we're multiplying that by minus 2. I'm not actually going to tidy that up because it's messy, but we don't need it. We're not asked for that algebra. We're asked, we want to get the gradient. So the gradient here, we know what t is, so we can just substitute it in. I've rubbed out what t was, but we're looking at this point A, and we found in the previous bit what t is at A. Hopefully if you wrote it down, you remember what it is. So t was 2 at A, so we can put that in there. And so we'll get 4 times 2 is 8, minus 8 log of 2. So that's the gradient of the curve at point A. We want the gradient of the normal, so we want the perpendicular gradient to that. So we need to flip it, get the reciprocal, and change the sign. So it's going to become positive, and we're going to take 1 over that. So the gradient, I'll call it m, will be 1 over 8 log of 2 for the normal. And we also know the coordinate that passes through, which is 0, 3. So I'm going to use y minus y1 equals mx minus x1, or you can use y equals mx plus c, whatever you use to get the equation of a straight line. So I'm going to use this one here, y minus 3 equals the m, the gradient is 8 log of 2, and then x minus the x coordinate, which is 0. And I'm not going to do an awful lot to this, I'm just going to leave it like that. Y minus 3 equals x over 8 log of 2. That is the equation of the normal to the curve at A. That example was really deeply rich in lots of different skills, wasn't it? So well done if you followed it, and if you did struggle on any of those elements that were brought together, then that's a great opportunity to know what you need to practice more. So hopefully that was a very useful example. Let's take a look at another one. Okay, I did say this was going to bring together a lot of knowledge from different topics, so of course it's got to practice some trigonometry. Trigonometry is quite popular in this topic, so let's have a go. And we're practicing some other things in this question. We're going to find where the gradient of the curve is a half, so that's using differentiation again. And we're also going to look at this time turning it into the Cartesian equation. So kind of similar to what I did at the very beginning of the video, we'll take a look at that. So first of all, we're finding where the gradient is a half, and we're going to differentiate for that. Again, we're going to do it the same way as the last question. Differentiate both of these separately and use the chain rule to connect them. So please do have a go. Okay, so I've differentiated those separately. Hopefully you got the same. And then connecting them with the chain rule, using theta this time. Okay, and sine divided by cos is, as you know, tan. I'm going to rewrite that as tan. And we want to find where all of this, the gradient, is a half. So I can set that equal to a half and then solve it. So I've got the tan theta is 3/4, and using the inverse tan of 3/4 on the calculator, I get that theta is 36.87 degrees. And literally, as I wrote that, I realised we're in radians. But never mind, no one needs to know because we're not using that as a final answer. You can still use that in your calculator because that's not the final point. We're just trying to find the coordinates, the x and y coordinates, so we can put them back into here. So as long as your calculator's in degrees the whole time, it'll all come back out again, don't worry. You can of course do it in radians if you're going to be proper, But let's put these back into x and y to get the coordinates. So putting them back into these equations here, I get that x is 3.8 and y is minus 0.6. Brilliant! Well done if you got that. Okay, part B now, the really fun part, is finding the Cartesian equation. I've just realised that I meant to show you how to find the Cartesian equation for these kind of equations, and I can't be bothered to go back and edit in the previous question, so I'm just going to do it aside now because it's slightly different. So these are the simpler ones. When you've got t as your parameter, then it's very easy to combine them to get rid of t. So when we're finding the Cartesian equation, we want just an equation with x and y without that parameter in it. So eliminate t. And that's quite easy to do for ones that look like this. All you need to do is rearrange that equation to make t the subject and then substitute it into the other one. You can do it for either way round, but this one's probably easier. So we can make t the subject here. So we'll get two lots of 1 minus x, and then literally you just put it in, replace the t in the other equation, and that is it. I'm not going to even simplify that, I'm just showing you how to do it. Very, very simple. But we don't have those simple equations here, we have trigonometry. So, a little bit harder, because you can't make sine the subject and substitute it in here. That's a bit tricky. So what you need to do if you've got trigonometry is use the trigonometry identities, and I showed you at the very beginning of the video, I showed you how to do that using sine squared plus cos squared is 1. So you need to think through your trig identities until you find one that will work with what you've got. So if you've got tan and sec, for example, you'll use the identity that involves both of those ones. Here we've got the basic sine and cos, so we can use sine squared plus cos squared is 1, like we did at the beginning. So all we need to do is make sine theta the subject and cos theta the subject of these equations, and then substitute them into the identity. So let's rearrange the x equation first. We'll have sine theta is x minus 2 all divided by 3. And rearranging the second one, now we can substitute them into the identity that sine squared plus cos squared is 1. So this squared plus this squared is 1. And this will be, it looks a little bit like a circle, doesn't it? But it's a funky circle. It'll probably be more of an ellipse. So that's the Cartesian equation of that curve. Okay, let's look at one more example. Okay, we're going to finish with more trig, and we're finding the Cartesian equation. So again, we're practicing using trig identities to combine these together. Now, in the last one we had sine and cos, which we could easily put into sine squared plus cos squared is 1. Here we have sine and we have cos of 2 theta. So I'm going to use the double angle formula here. Let's just remember what that is. You need to know it off by heart, I think. There are 3 versions, and we want the one that's most relevant here. We're going to be using sine here, so I'm going to use the one that's just involving sine. So that's that. So it would make sense to make sine theta the subject of that equation up there. So now we can replace cos 2 theta with this and replace sine with that. Oh, let's do it in 2 steps. So we're taking our y equation, 1 plus cos 2 theta we know is this, and that's all over 3. And then we can replace the sine with x minus 3 over 4. Okay, this just needs tidying up then. That's a bit messy, but it shouldn't be too hard to tidy this up. We can bring the 3 up to be with the y, and we can expand these brackets out. I can cancel a 2 on here with the 16 down there to make that 8. And then if you really want to, you can turn that 2 into a 16 over 8 and then put that on the top with those guys. So it would be 16 minus all of that. And I'm going to remove the brackets and change the signs of all these things. 6x. So we'd have a minus 9 and combine that with a 16 to get 7. So that's the Cartesian equation of the curve. 3y equals all of that stuff. You can get that into a different form if you want, but that's it. I've also put to find the domain as well, just to have a look at domain and range quickly. So the domain is just the x values, and we know that theta, it takes on these values here, maximum and minimum. So if we just put them into that equation, we'll get the x values. So putting them into the calculator, I get that the minimum is -1 and the maximum, putting pi over 2 into here, is 7. And that makes sense if you wanted to sketch yourself a graph of the x with the theta values, going from pi over 2 to minus pi over 2. If you wanted to sketch that using your graph transformations, normally sine fluctuates between 1 and -1, but this will get stretched by a factor of 4 in the y direction and then moved up 3. So yeah, I get, if you think of it that way, you get the values -1 and 7, and it would look something like that. So that's the domain. Well, I hope this video was helpful. I hope it gave you a flavour for some different things you can do with parametric equations. Keep practicing lots of different examples and have fun. Thank you for watching.